NASA plans to switch on a nuclear reactor on the moon, and it wants to do it by 2030. But this will not look like any nuclear power plant you have ever seen. There will be no concrete containment building, no giant cooling towers, no river carrying away excess heat, and almost certainly no astronauts standing outside with tools, trying to assemble nuclear equipment while wearing pressurized gloves. Instead, the entire power plant could arrive from Earth as one compact, folded machine. After landing, a robotic rover may remove it from its spacecraft, carry it away from the astronauts, position it behind a lunar ridge, unfold enormous cooling panels, and roll a high-voltage cable all the way back to the base. Then, once every human is safely out of the way, controllers will attempt to bring the uranium core to life. But strangely, splitting uranium atoms may not be the most difficult part. The real challenge will be stopping the reactor from slowly cooking itself. Because the moon has no cooling water, almost no atmosphere, and nowhere convenient for all that heat to go. And if NASA can solve that problem, this machine could transform the moon from a place humans briefly visit into a place where they can actually stay. NASA calls the project Lunar Reactor 1. The reason it is needed begins with one brutal fact. Night on the moon can last for more than 14 Earth days. Solar panels can generate electricity while the sun is visible. But when darkness arrives, a lunar base must still circulate air, heat its equipment, communicate with Earth, recharge vehicles, and keep every astronaut alive. Batteries can handle short interruptions. But 2 weeks of darkness is an entirely different problem. During the lunar night, temperatures in some regions can fall toward -200 degrees Celsius. If the power fails, the astronauts will not simply lose the lights. Water pipes could freeze. Electronic systems could shut down. Life support equipment could stop working. And a habitat designed to protect its crew could quickly become uninhabitable. NASA, therefore, needs a power source that does not care whether the sun is shining. That source is nuclear fission. The current goal is to build a reactor capable of producing at least 100 kilowatts of electricity. That would not be enough to power a giant lunar city, but it could support habitats, communication systems, scientific equipment, robotic vehicles, and machines that process lunar resources. More importantly, a reactor could operate inside permanently shadowed regions. These are places where sunlight may never reach the ground, but where large deposits of frozen water may be hiding. That ice could eventually become drinking water. It could be separated into oxygen for breathing. And one day, its hydrogen and oxygen could be used to manufacture rocket fuel. But before NASA can use nuclear power on the moon, it first has to place a nuclear reactor on top of a rocket. That sounds dangerous. The important detail is that the reactor will launch switched off. Its nuclear fuel may already be installed, but the core will remain unable to sustain the chain reaction required to generate power. The reactor will not operate during launch. It will not operate during the journey. And it will not operate during the landing. Only after the machine has safely reached the lunar surface will NASA attempt to start it. And no, a rocket explosion would not cause the reactor to detonate like a nuclear bomb. A power reactor and a nuclear weapon use completely different fuel arrangements, designs, and operating conditions. The rocket could explode, but the reactor would not suddenly transform itself into a warhead. Once the lander reaches the moon, the real construction process begins. Imagine a cargo spacecraft descending near the lunar South Pole. Its engines blast the surface, throwing dust across the landscape. The lander touches down, carrying a compact nuclear system that has never operated beyond Earth. A robotic rover approaches. It connects to the reactor package, carefully removes it from the lander, and begins driving away from the future habitat. This distance is critical. An operating nuclear reactor produces neutron and gamma radiation. NASA could surround it with enormous amounts of metal shielding. But shielding is heavy, and every kilogram carried to the moon consumes valuable launch capacity. So instead, NASA can use something much cheaper: distance. The rover may carry the reactor hundreds of meters away from the astronauts. It could position the machine behind a ridge, a crater wall, or an artificial mound of lunar soil. That terrain would block the direct line of sight between the reactor and the habitat. The reactor may also carry a directional shield, protecting the inhabited side without completely surrounding the machine in heavy material. In other words, the moon itself could become part of the radiation protection system. Once the rover reaches the selected location, stabilizing legs lock the machine onto the ground. Antennas rise. Power equipment unfolds. And then the largest part of the entire structure begins to open: the radiators. A nuclear reactor does not produce electricity directly. Its first product is heat. NASA plans to use that heat in a system known as a closed Brayton cycle. The reactor heats gas inside a sealed loop. That hot gas spins a turbine. The turbine drives an electrical generator. The gas is then cooled, compressed, and sent back toward the reactor to be heated again. Nothing needs to burn. No oxygen is required. And the working gas is not released into space. It circulates through the same sealed system again and again. But only part of the reactor's heat becomes usable electricity. Everything else becomes waste heat. On Earth, power stations can dump that heat into the air or water. They can use rivers, oceans, cooling towers, fans, and huge steam condensing systems. The moon offers none of those things. There is almost no atmosphere, meaning heat cannot be removed through normal air cooling. There is no nearby river. There is no wind blowing across the machinery. The reactor can remove heat mainly by radiating infrared energy into space. And to radiate large quantities of heat, the system needs a large surface area. A very large surface area. That means the reactor core itself may be relatively compact, while enormous radiator panels stretch outward across the lunar landscape. The machine that arrived folded inside a lander could transform into a power station tens of meters wide. And now NASA faces another problem: lunar dust. Moon dust is not like soft sand on a beach. There's no flowing water or wind on the moon to smooth the particles. The grains remain sharp, abrasive, and electrically charged. They stick to machinery. They scratch surfaces. They work their way into mechanical systems. And if enough dust collects on the radiator panels, it could make them less effective at releasing heat. The reactor could land successfully. The turbine could start spinning. Electricity could begin flowing. And then electrically charged dust could slowly attack the cooling system, preventing the machine from overheating. NASA may need protective coatings, electrostatic cleaning systems, robotic brushes, and extra radiator capacity. Because on the moon, even the equipment designed to clean the reactor may need its own backup. Assuming the reactor remains cool, NASA still has to deliver the electricity back to the astronauts. Moving the reactor away from the base helps solve the radiation problem, but it creates a transmission problem. NASA may use a rover to unroll a high-voltage cable across the lunar surface. The cable could stretch for hundreds of meters, possibly even farther, connecting the remote reactor to the habitat. High voltage would help reduce electrical losses. But the cable would have to survive extreme temperature changes, abrasive dust, sharp rocks, radiation, rover traffic, and micrometeorite impacts. A single damaged section could leave the reactor operating perfectly. While the lunar base receives no electricity, nuclear physics, defeated by a broken extension cord. Once the reactor is deployed, cooled, shielded, and connected, the final startup would happen remotely. Control systems would gradually allow the nuclear chain reaction to begin. Sensors would monitor neutron levels, core temperature, turbine speed, radiation, and electrical output. Power would increase slowly. The reactor would not instantly jump from 0 to maximum capacity. And after startup, the machine would need to operate largely by itself. It must detect faults, adjust its output, protect its equipment, and shut itself down safely if something goes wrong. Astronauts cannot spend years standing beside a nuclear reactor making manual adjustments. The power plant must become one of the most autonomous machines ever placed on another world. And when lunar night finally arrives, the reason for building it will become clear. The sun disappears. Solar production falls. The landscape turns black. Temperatures collapse. But inside the habitat, air continues circulating. Water remains liquid. Communication systems stay online. Scientific equipment continues operating, and electric rovers recharge for their next journey. The astronauts may be asleep, while somewhere beyond a distant ridge, uranium atoms continue splitting inside a machine. The first reactor will not power a futuristic lunar metropolis, but it could power the machines that eventually build one. Continuous electricity could support robotic excavators searching for ice. That ice could become water, oxygen, and fuel. Reactors could power construction vehicles, processing plants, laboratories, communication networks, and eventually the first electrical grid beyond Earth. The 2030 deadline is ambitious. NASA and its partners must still finalize the reactor design, qualify the nuclear fuel, test the power conversion system, complete safety reviews, integrate the machine with a lander, survive launch, land it on the moon, and deploy it autonomously. But the larger idea is even more ambitious. Every crewed lunar mission in history has arrived carrying a limited supply of energy. Astronauts landed, completed their work, and left before the lunar environment overwhelmed their machines. A nuclear reactor changes that relationship. It means the lights do not have to go out when the sun disappears. It means robots can continue building through the lunar night. It means the moon can begin producing its own resources instead of receiving everything from Earth. Lunar Reactor, one would not simply be a power plant placed on another world. It could become the first piece of permanent infrastructure beyond Earth. And the moment that reactor switches on, humanity will no longer be visiting the moon with batteries. We will be powering it. Subscribe for more stories about the machines, missions, and technologies that could build humanity's future beyond Earth.